Right, it's right at the top of the hour. Good morning, good afternoon, and good evening, depending on wherever you are joining from. Welcome to our special COVID-19 session number 38. This is a series of sessions that we have dedicated to diagnostics in the COVID-19 pandemic. Today we have an exciting topic titled Impact of Novel Variants on COVID-19 Diagnostics. As we have all known, these variants have come through, and as Prof. Wendy said on Tuesday, may not be a good idea to call them by their countries, but they've actually spread right through the world in various forms, and we continue to fight the pandemic nearly a year and several months down the line. Today, we are going to be focusing on how the emergence of these new variants are affecting the pandemic, the potential of these variants on current COVID-19 tests, as well as launch an important document that has been developed by FIND and ASLM. This is a document, a PCR guidance on in-house test development for molecular detection of SARS-CoV-2, which is also critical when we talk about elements like variants. To do this, we are honored to have three presenters today in the name of Professor Christian Happi, who is a professor of molecular biology and genomics at Redeemer University, and also holds directorships in important units as well. We also have Dr. Jilian Sachs from FIND, who's the head of Preparedness at FIND, as well as Devi Emparado, who's a scientific officer in the Pandemic Preparedness Unit as well. This will be a 1 hour long session that will be made up of those three presentations coming through, and we shall follow up with questions and comments. Keep them coming and we address them at the end of the session. I would like to remind you that there is there's a French to English language interpretation that is available, so please feel free to choose the language of your choice. Ladies and gentlemen, I am honored to invite the first presenter today, who is Professor Christian Happi, who is the director at the World Bank African Center of Excellence for Genomics of Infectious Diseases, ACEGID, as well as a professor at the Redeemer University Ede in Nigeria. Prof, over to you.
Okay, thank you. So Christian Happi is my name, as Anafi just mentioned. I'm the director of the African Center of Excellence for Genomics of Infectious Disease at Redeemer University. We're funded by the World Bank, but we are also one of the two reference, labs centers on the continent. WHO and Africa CDC continent on the continent when it comes to infectious disease genomics. So today I've been given the task to talk about SARS-CoV-2 mutation and the implication of diagnostic PCR. So as you know, as of 28th of February, so this is the case fatality, the number of cases of the situation in Africa, over almost 4 million cases, almost 3.5 million recovered, and over 1.3 million dead. As you can see very well, compared to the rest of the world, the situation in Africa is not as dire as it is elsewhere in the world. And I think is due to the combination of many factors. So one of those factors is the fact that, earlier on, after the Ebola outbreak between 2014 and 2016, Africa actually understood the importance of integrating genomics into disease surveillance, and especially when it comes to infectious disease outbreak and pandemic response. So, and then this was really spearheaded by the Africa CDC. And in doing this, they established what we call a network, for genomic epidemiology, or what they call the Pathogen Genomic Initiative in Africa. And then that network is leveraging so many things available on the continent. First of all, and leveraging the existing capacity on the continent. That network is made of countries that you see on this map. In East Africa, you have UVRI in Uganda, Cameroon, Kenya, RNB in the Democratic Republic of Congo, CRIPS in South Africa, and ACEGID. Then the Nigeria CDC, which is a regional lab. Then my own lab, the African Center of Excellence. Then Noguchi in Ghana. Then IPD, that's in Supasteur in Senegal, and in Supasteur in Morocco. So it is structured in the way that, you know, we have what we call national lab, we have regional lab, and then we have what we call reference lab. And then the reference lab are what you see in blue here, the ACEGID and then CRIPS in South Africa. So those are the two continental reference labs, the others are regional and then national lab. So that network actually, you know, it really, the pillars are 5: mobilize resources and then start simple to establish routine surveillance. Then the third one is actually to support sample collection and shipment and logistics. So for many of you know, this is happening on the ground at the moment. Then also support sequencing reagents and equipment and upgrade, you know, and equipment upgrades and personnel, and also support data analysis and sharing and interpretation. So, and then the structure is such that it is coordinated by the WHO and African CDC, and then the operational framework is such that you have here we have the reference lab, so, and then we have 1 bioinformatics center, and then 2 reference lab, CRIPS, and then at the ACEGID, which is my lab at University. Then below it, we have the regional lab that you see over here, and then you also have the national labs all across the continent. So this is a structure that the African CDC really leveraged in order to have this integrated into the public health response to COVID in Africa. So, and then when the first case, you know, of COVID in Africa occurred, that was in February 26 in Nigeria. So Nigeria really leveraged the facility that already existing, and the Africa CDC leveraged the facility already existing in our lab, as you can see here, you know, robotic for extraction, and then also and sequencing, and also leveraging things like, you know, like a Novasec that can do like almost 6,000 samples per run, you know, in our lab. And this exactly what we did in the first case by leveraging some facility to sequence the first SARS-CoV-2 genome in Africa. And this was really done at the speed of light, as we say, you know, within 48 hours of receiving the sample, and then releasing the sample in GISED. So this was unprecedented. So we were able to not only to know that the sample of the virus was, a foreign introduction into Nigeria, but we were able to locate exactly where this patient was infected. You could see here clustering with sample from Switzerland, even though that patient was from Italy. So that really actually paved the way for additional sequencing subsequently across the continent. As you could see here, for instance, we were able to clearly demonstrate, you know, apart from just doing sequence, as you can see, the first cases reported in different countries, but we're also to use, you know, genomic sequences to start showing clusters of community transmission. So you could see here, like the case in South Africa, where you see clearly, you know, a very close, you know, proximity between the first case and clusters of transmission. Even though in Nigeria, for instance, where we had the very first case in Africa, then you could see that we identified clusters of transmission further down the line. And this really provided very useful information, you know, for people. But as time went on, as you could see, Africa has really been has produced, you know, quite a number, probably not as much as the rest of the world, but at least we've been able to do at least almost 5,500, you know, good quality, you know, data sequences across the continent. But as you can see through this table, you can see that most countries in the continent, you know, are generating and producing sequences. Not that all these countries do have facility to sequence, but they're actually leveraging, collaborating, sending sample to sequencing centers so that they can produce. And then as recent, you could see, as other countries that produce, you could see countries like Rwanda, RDC, Congo, Nigeria actually producing a huge number of data out there. So this really, you know, leveraging facilities are available. And then this exactly is what we expect from the African continent. That is collaboration and leveraging whatever is available in order for all of us to respond efficiently, you know, to this outbreak. You know, and then what we can take out from all of the sequences done across the continent, as you see so far, is actually that, you know, most primary sequences in Africa were introduced through, you know, were imported. And then we can see through the analysis done in our lab that we have over 1,000, about 1,500, if not more, different introduction in Africa, but mostly from Europe, but also from Oceania, Asia, Oceania, and America. And then the reason for Europe, mostly because there's a lot of traffic between Europe and Africa in terms of commerce and businesses and travels. So this also helped a lot by helping countries to navigate internal outbreaks. So this is a case of South Africa, where they actually established within country a network, a genomic surveillance network that helps South Africa to be on top of the situation and then uncover new variants way ahead of the spread. In Nigeria, we also had the same situation whereby we use genomic. You could see Nigeria is a country of 37 states, but we've really mapped 25 out of 37, so far. But I think this map is a little bit old because right now we've almost covered the whole country. But really being on top of the situation, also having an idea of what is going on in the different parts of the country. And these informations are often given directly to public health, institute or public or decision makers, so that they can actually use them as evidence to actually do the necessary policies. So for instance, this is a case like in Nigeria, for instance, where we know that at present we have 55 different lineages circulating in the country, but then we've been able to establish that in real time. As you can see, if I click on the screen, you can see how we're picking this in the country, and in real time with time and with date and time, you can talk with the dates and then how this is spreading across the country. And this is kind of dashboard that we put in place in order to actually let those in decision-making position see the evidence as things are evolving. So in the case in South Africa, you could see over time how some of these lineages get introduced and then they actually take over, as time goes on. And you can see, for instance, like we don't call it South African lineage, but this emerging lineage, B1321, that appeared in South Africa, really appearing at some point last year and then taking over as time goes on. And this really credit to Tulio and his group and then the consortium in South Africa, to actually show genomic epidemiology into action. Well, this is another example to show you how we do this. I mean, how this, for looking at the spike mutation, this is a case, for instance, in Nigeria. So one of those first groups to actually identify the spike mutation were early in 2020, in the beginning of the outbreak, but you could see how this mutation is really taken over. And then this mutation, as you know very well, has been associated, with increased transmission and increased transmission. So really using this kind of approach to monitor, not only mutation, but also to look at the temporal spread, actually can provide a lot of information to the way we're doing things. But then the spike mutation spread across Africa can give you, this is not just in the case of Nigeria, but this gives you an idea of this is how this mutation really spread across the continent. And you can see across the continent that it is a mutation that has really taken over. So based on our own analysis, you can see most countries or most variants circulating in various countries in Africa really have this particular mutation. That is a D614G mutation that has been associated with increased transmission. But then later on in South Africa, when South Africa was facing almost the second wave, then you could really see the emergence of this variant, the B1351 mutation, a variant that has been associated with, a reduced potential to reduce vaccine efficacy. And then this is a variant of concern, obviously, but then this is a product of genomic epidemiology in action. So, and then these are all the mutations that you could see on that particular variant, and that provides very critical information in terms of not just the genomic epidemiology, but also has ramification in terms of, vaccine efficacy and then potential diagnostics. So, and then using such a collaborative approach, as I mentioned before, you could see that this variant that was discovered in South Africa, for instance, found its way, for instance, in the Mozambique. And this is a collaboration between Mozambique and South Africa, whereby samples get to South Africa and then they were able to sequence. And through this, you could see, three major clusters of community transmission. And that really tells a lot that this variant is already embedded into the communities and is spreading. So, and then this is really, thanks to Tulio, who shared this slide with me, and that really shows clearly how you can leverage collaboration and use some of these mutations as a way to actually monitor the transmission and spread of variant across the continent. Now, when the UK actually mentioned the B117, which is the variant of concern concern in the UK, we experienced in Nigeria, for instance, a spike in the number of cases that was around December. And we really started looking at, what could be responsible for the spike. And then earlier on, so we we identified this particular variant in Nigeria, and these numbers are a little bit outdated because they are much more than these numbers as I mentioned here. But then that really gives you an idea of how these mutants, or these lineages or these variants are basically emerging, or they are, either in the case of Nigeria, we believe that it could be what I call de novo mutation, or imported. So we basically believe that then they give you the structure of that particular that particular B117 variant. But what is interesting about that, for instance, looking at the age distribution of that variant in Nigeria, is a large chunk, if not a larger number, of these patients are young people below the age of 30 years. And that for us really is important. And then you could also attribute this to the fact that this might be related to high exposure, and high exposure might also be related to kind of the occupation nature of this particular, of this group of people. So then that tells you that epidemiologically, you don't want to just look at the most vulnerable group, but you also want to look at, occupation, that could be a population that is probably driving the epidemic. So but then recently we discovered a new lineage, this is a B1525 in Nigeria, but then this lineage that is also kind of raising some concern because of this new cluster that you see here. And then what that new cluster is doing is basically because it's harboring this particular mutation, which is the E484K and then the Q667H. And all of these mutations, find themselves in the pocket that is probably that is targeted by some antibodies that are actually what we call neutralizing antibody, and this seems to be affecting the way this neutralizing antibody are attacking the virus. So we found this earlier on, and then we believe this mutation emerged, or this variant emerged from Nigeria because it's the oldest so far in the database. And then we also realized that these are spread to many other states. So we initially were about 5 states, but I think the number is about 7 or 8 now, and which means that it is also already into those communities and is spreading. So, and we believe that although it's not been described as a variant concern, but then there, some report are, definitely raising some eyebrows in the fact that the E484K mutation actually has seriously, has the potential to affect the class 1 monoclonal antibodies. And I think a recent publication from Tulio in Nature Medicine, that I had the privilege to review, actually confirmed that as well. So that really, it shows here how we could use, genomic as a way. But now to bring down to the point of this one of the major points of this meeting today is actually how this mutation could affect diagnostics and PCR. So this is one analysis that we did, for instance, to look at the different set of primers that are available out there, and then look at the mutations that could be look at the mutation into the primer targeted site. And you could see here, this is a China CDC primers, and then you could look at the level of mutation. So really, then the worry about this is that once you have this level of mutation accumulated in that site, and it tells you that the probability that you're going about having primers not binding properly and then leading to false negative might be a major concern. So if you look at orders over time, look at the CDC, US CDC primers, N1 and 2, and then the Pasteur Institute and then the charity primers. So we take a stab at those, and then we can see that over time, these targeted sites are accumulating mutations, and then the risk as this one increases is actually the fact that, we may end up not having the primers annealing properly, and then that results in false negative even when somebody's infected. But then when we look at those mutation closely, you realize that this pattern that we observe here is not uniform across country. This is based on Nigerian sequences here. But if you look at this, we sequence some sample from Cameroon, and if you look at the pattern of this mutation accumulation around those primers targeted area, you could see the Cameroon, which is neighbor to Nigeria, but their patterns are very different. So you could see here in terms of all of those primers, in Cameroon, they're accumulating, so they're under different selection pressure, and then they're evolving very differently. And you can see that in this environment, those are under stronger selection, and then you have more accumulation of mutations. So then the lesson here is that this has to be monitored in every environment or each country very seriously, so that we know, because you don't expect this to be the same all over the place. So and then really I just wanted to end this talk somewhere here, so that because this really, so that the other presenters could dovetail into this introduction so that people can see. So in conclusion, so basically genomic surveillance is critical for epidemic response. And then you could see the very beautiful example in South Africa to characterize and tracking, this new variant, and also in Nigeria, for instance, where we discovered this variant and then could show that it was imported from Nigeria and out to outside Nigeria. So we identify, new lineages with multiple mutation at key sites in spike protein. But then the key also here is that the mutation in the primary or binding site could lead to false negative PCR result. And then it's just really critical, to monitor those target sites, by genetic or genomic sequencing. So at this point, I really want to thank you again for the opportunity, and then really acknowledge my funders and then my partners and then the people, all of these young guys doing all the work in my lab. And really, again, I am looking forward to a fantastic session, and thank you. Over.
Thank you, Prof. We are honored to have the expertise on the platform. Very insightful information that you bring to us. Indeed, we are learning a lot of collaboration continues to go. The Mozambique and South Africa examples, how the spike protein has actually sort of taken over the continent. And to summarize it, I would quote you, I think this is really genomic epidemiology in action. But what is the impact on diagnostics? You touched on that a little bit. And to unearth that, I would like to call upon the second presenter today, Dr. Jilian from FIND, to come and give us the next presentation. Over to you, Jilian.
Great, thank you. Hope you all can hear me. So thank you to ASLM for the invitation to speak today. And I'll kind of just take a bit of a step back from some of the great information that Professor Happi just shared with us to talk about the impact of the novel variants on COVID-19 diagnostics. Great, so as Prof. Happi already alluded to, the variants that we're discussing today and that are so much top of mind right now all arise through the natural process of mutations in the viral genetic sequence of SARS-CoV-2. And these mutations can have impacts not just on the molecular nucleic acid tests that we mostly use to diagnose COVID-19, but can also have impacts on the antigen tests as well as the serological tests that might be in use. So for the nucleic acid tests, the alterations in the viral sequences that are targeted by the primers of these particular assays can lead to lack of correct binding and then decreased sensitivity of the particular nucleic acid test. As well, mutations in the viral genome can perhaps lead to causes to changes in the structure of the antigens that are targeted by the antigen detection assays, which could also negatively affect their performance. And then finally, alterations in the viral genome that cause changes in the structure of proteins may also result in changes of the antibody repertoire that is elicited by the host who's infected by SARS-CoV-2. And again, this could then impact the accuracy of the serological assays. So just briefly, the genome of SARS-CoV-2 is relatively simple. The S gene encodes the spike protein, which is the one that we talk about the most for viral entry and where a lot of the mutations associated with the many variants are occurring. But there are other genes within the genome that also are accumulating mutations that are found within the variants that we'll be discussing today. So there's 3 variants of concern that have been identified thus far. There's B117, B1351, and P1. They each have several different characteristic mutations that are associated with each of the variants. They were discovered originally in different countries. And as mentioned previously, the number of mutations that are in the S gene vary, but this is the region that seems to be accumulating the most mutations. So on the African continent thus far, there are at least 2 countries that have detected at least 10 cases of B117, that's Ghana and Nigeria. Thus far, there are no reported cases of P1 yet in Africa. And then B1351, which was originally detected in South Africa, obviously the countries with greater than 10 cases are all concentrated more in the Southern African region, although there are cases that have been reported across the continent. So as Prof. Happi already introduced, there is a new variant under investigation that was first discovered in Nigeria. It is not yet considered a variant of concern, but because it shares several mutations with B117, B1351, and P1, and as Prof. Happi mentioned, there may be impacts on the generation of neutralizing antibody in response to this variant. It's an important space to watch to see if this does get characterized as a variant of concern. So I'm just going to go through in the next few slides each of the different testing platforms and how the SARS-CoV-2 variants might impact their performance. So for molecular tests, thus far, because most of the nucleic acid tests that are in use target multiple genes, the impact of any specific variant is currently expected to be minimal. There is currently no reports of the molecular tests that are in widespread use being dramatically affected by the new variants, except for there is, for B117 at least, the observed lack of detection of the S gene target, which is also termed the S gene dropout. But because most of the assays that target the S gene also target other genes within the viral genome, you can still diagnose SARS-CoV-2 effectively. So laboratories should routinely review their testing data for unusual or unexpected results, including monitoring for these targeted gene dropouts. So I just listed here the 4 different variants, the 3 variants of concern and the new B1525, which also does have the deletion at position 69 to 70. So perhaps you might also observe the same S gene dropout if you were using an assay that targeted the S gene, whereas B1351 and P1 don't have that dropout. For the antigen tests, as of right now, the impact is expected to be minimal. Most of the antigen detection tests target the nucleocapsid protein and specifically target the C terminus of the nucleocapsid protein. There are a few antigen tests that are in use that target the spike protein. Those that do target the spike protein might be more impacted by the variants. And so I've just summarized here, there has been some initial data generated by Public Health England looking at 6 different rapid antigen tests and their performance in detecting B117 and B1351, and they found minimal impact. There hasn't been experimental data yet that I'm aware of that's been published on the performance of the antigen tests in detecting P1 or B1525, but again, the expectation is that there will be minimal impact. The impact of the SARS-CoV-2 variants on serological test performance is likely to be a bit more complicated to sort out. So as I said, these assays do not directly detect the virus, as you know, but rather the immune response that's generated to the infection. And so it's likely going to take a bit longer to ascertain how the immune response differs in individuals infected with the variants, and then how that might impact the performance of the different antibody tests. To date, there has not been any publicly available systematic evaluations on the many different serological tests that are commercially available. But since there is initial data showing that the immune response to these variants does differ, there may be impact on the serological tests. But I will note that because many programs only use antibody tests for seroprevalence analysis or epidemiological studies, and rather than primary diagnosis, hopefully these variants won't have a huge impact on the use of these tests for diagnosis. So different test regulatory agencies have issued some information. So the US FDA, for example, has issued some guidance for molecular test developers who are pursuing emergency use authorization in the US as to how they can mitigate against the impacts of these mutations on their tests. So they suggest, obviously, that suppliers try to design tests that minimize impact of the mutations on their test performance. So they ask test suppliers to now consider their performance across all known variants at the time of whatever validation they're performing when submitting their test for emergency use authorization to the FDA. This guidance does describe some suggestions on how to design the test to mitigate this risk, including having multiple targets, obviously, and the suggestion that including highly conserved targets may improve performance, but that obviously the number of targets of the test should be appropriate to provide resilience. They suggest that suppliers should periodically conduct sequence alignment of their primary and probe sequences with the available SARS-CoV-2 genomes, also known as an in silico analysis. And then if that analysis shows that the mutations reduce test performance by at least 5%, then the supplier should contact the FDA. Similarly, if there's observed to be a difference of greater than 3-fold in the limit of detection, the supplier is asked to prepare a risk analysis and again to notify the FDA. And then obviously if there are any differences in performance across the variants for a particular assay, suppliers are requested to specifically note that information in their test labeling. There's similarly some guidance for antigen detection as well as antibody detection assays from the FDA, although the right approaches for assessing the impact of the variants on these two different types of products is still being better elucidated. And I've shared here the link for the full guidance in case anyone is interested. Finally, WHO in January issued guidance to end users. So rather than focusing on the companies, this is focused on you all as laboratorians and testers. And some of this is relatively straightforward. So obviously as part of your routine QA and QC procedures, you would be routinely reviewing testing data to look for changes. So some of the routine data that you might want to look at are positivity rates, which of course vary over time, but any sharp changes might indicate that a variant is starting to emerge. If there's any significant changes in your invalid rates, or specifically if you start to detect dropout or discrepant detection across the different gene targets for the assays that have multiple gene targets, those are also things that should be noted. And then as per routine post-market surveillance activities, if you notice some of these routine changes in an assay that you're using, you should notify suppliers of any of these unusual results. So some specific data that you could notify suppliers of would be increased discrepancies in the CT values across different gene targets, failure to detect specific targets, or if you have instances of actual misdiagnosis that you're concerned about. And again, I put a link to this full information note for those of you who may not be aware of it. So finally, I was asked to touch on company responses to mutations in SARS-CoV-2 and the variants of concern. And obviously, there are so many different companies that have manufactured and commercialized assays for the COVID-19 diagnosis. So I'm just showing here 3 examples from companies. This is just meant to be illustrative and in no way is exhaustive, but I'm just showing here some language that 2 companies, Abbott and Cepheid, have shared, which related to their molecular assays, and then information that was shared by SD Biosensor, which manufactures an antigen detection assay. So most companies have generally conducted in silico analyses looking at whether the sequence of the variants are expected to have any impact on performance of their particular assay. And then they've issued letters to customers or posted information through press releases and or information on their website. I'll say FIND is trying to start compiling all the different official correspondences from companies, and we're hoping to eventually make that available on our website as well. So here's just some example language. So you can see Abbott did a bioinformatics analysis for their 3 molecular tests on the Alinity platform, or the M2000, and they noted that their analysis shows that none of these 3 assays would be impacted by the new variant strains. Similarly, Cepheid did an in silico analysis and showed that coverage is currently 100% for their E gene target and greater than 99% for their N2 target. And they also are compiling data from customers. And so they're saying that the Expert Express can still be used to presumptively diagnose individuals with SARS-CoV-2. And then finally, as I noted for the antigen detection assays, since this company noted that since the recognition site of their assay targets the C-terminal side of the nucleocapsid protein and that the mutations are all in the N-terminal side, that they do not expect any performance impact. I think it is of note, though, that I think a lot of different groups right now are starting to culture these different variants and do some limited wet lab analyses to look at, to confirm that there are, in fact, no substantial impacts on performance. And so I'm guessing there will be data emerging on this in the next few months. So just to summarize, analysis of the specific mutations carried by the novel variants suggests that the majority of tests currently used in primary detection of SARS-CoV-2 should not be greatly infected, but it is really important that testing programs and laboratories are aware of potential effects and that you can take action should you start to be concerned that there is a compromise in performance of the assay that you're using to diagnose SARS-CoV-2. Obviously, as part of routine QA/QC procedures, end users should actively monitor test results trends. And as Prof. Happi very eloquently pointed out, the rapid emergence of these variants really demonstrates the need for robust and widespread genomic surveillance so that we can ensure that other novel mutations are detected promptly and appropriate action can be taken. And it is important to continue to monitor diagnostic test results. So with that, I'll thank you for your attention and the opportunity to speak today, and thank many of my colleagues who helped put together this presentation. Thank you.
Great. Thank you very much, Jillian, for the wonderful presentation. Indeed. So variants, the virus never stops mutating. Diagnostics are trying to keep up. Regulatory units have also not stopped. They have also issued some guidance. WHO has also taken the lead and issued also guidance. And even at individual level, at institution level, at lab technologists and lab professionals level, also everybody has a role to play. Jillian mentioned QA, QC. So to move on, we would like to move on to the third presentation, really linking to the last part that Jillian has mentioned. What expertise is really required to be setting up a PCR in your lab. ASLM and FIND found it very important to try and come up with a guidance on in-house test development. And I would like to call upon Devi Emparado from FIND to come upon and give us an overview of what this guide is all about and what we intend to, which route we intend to take going forward. Devi is a scientific officer in the Pandemic Preparedness Unit at FIND. Over to you, Devi.
Okay, so thank you, Anafi, for the introduction, and thank you everyone for joining this call. So I have the pleasure of introducing the following resource, which Anafi mentioned was co-developed by FIND and ASLM on in-house test development for the molecular detection of SARS-CoV-2. So as a brief introduction, I think we're all aware of the purpose of molecular testing, and it's to detect the viral genome. We all are aware of that there are two types of molecular testing platforms. The first being more of a closed systems. So examples include the Cepheid Expert, the BioFire, etc. Now these systems are proprietary test systems, which means that all of the accessories are sourced by the manufacturer and that there is a standard procedure for testing, making testing fairly easy and more accessible. However, a challenge is when a laboratorian may not be able to program or use different test accessories that are sourced from different manufacturers. And so the other type of molecular testing platform is more of an open system, which benefits from being able to accommodate different kinds of tests from multiple manufacturers. And so I think we all appreciate that early during the pandemic, in-house lab developed protocols were key in the detection of SARS-CoV-2 and are one of the first key tests to respond to outbreaks of emerging infectious diseases. And so knowledge of the steps to develop an in-house lab developed test may not be readily available, or a refresher is needed for laboratorians in the continent. And so the team at FIND and ASLM had aimed to respond to this need, and so came to develop this guide, as you see here, called the In-House Test Development for Molecular Detection of SARS-CoV-2. And so the purpose of this guide is to provide guidance on the development of new in-house real-time RT-PCR tests for SARS-CoV-2. However, the way that the document is written, it includes information that allows and provides a roadmap for the development of new molecular diagnostic tests for other emerging pathogens. The guide itself has highlighted and thought of considerations for the constraints that I think we all appreciate and feel, especially in resource-limited laboratories. And the guide is available in multiple languages, so English, French, and Portuguese. So I've included here a link to the guide in case you'd like to check it out and read it as I'm discussing right now. And so the contents of the guide, there are really two main themes that are addressed, and it's divided between protocol development and validation, as well as diagnostic testing and quality assurance. And so for the first step, it's all about how to make a test. The second topic, how to implement this test. So under protocol development and validation, it includes the steps needed for how to design your PCR tests. So what's required, resources, equipment, an overview of the assay process, how to design your primers and probes, as Prof. Happi and Dr. Sachs mentioned, will be incredibly helpful and useful in the context of detecting new variants of concern or checking to ensure that PCR tests can still detect new variants. It also includes a guide and guidelines for selecting your enzymes and controls. Also included in this piece is protocol validation. So what types of experiments and how to design your experiments in order to assess your performance of the test. So it includes assessing the analytical sensitivity and specificity. So that's your limit of detection and your ability to ensure you don't there are no cross reactivities of your assay, as well as the clinical sensitivity and specificity. And through these experiments, it includes guides on how to optimize your assay so that it is at its most optimal form to perform diagnostic testing. And then lastly, under diagnostic testing and quality assurance, this section really describes how to set up your laboratory and how to ensure that your testing workflow is ideal. So it includes discussions on lab biosafety, how your PCR testing workflow can look and should look within your laboratory. So looking at your pre-analytical, analytical, and post-analytical activities, understanding where test errors may occur and how to implement quality control, as well as how to implement quality assurance to assess how the laboratory as a whole is functioning and how your tests are functioning, especially given the new variants. And so lastly, as part of the ASLM Academy, ASLM, along with FIND, will be leading a more in-depth training based on this PCR guide that we've introduced. And so the goal of this course is to provide more of an in-depth, detailed discussion and walkthrough on how to develop a test and how to validate your test for molecular detection of SARS-CoV-2. I believe ASLM has already sent the link to register for this course, but you can check the link here to also register. And course certificates will be issued upon successful completion of the course and is free for qualifying candidates. So more information will be shared and provided by ASLM. And so with that, I'd like to say thank you for having me and for having us today. And I hope that you all have access to the guide and are able to use it even now in your laboratory.
Thank you very much. Thank you very much, Devi, for the wonderful presentation. Now we are moving on to the Q&A session. We still have a couple of minutes to take some of the questions. Keep them coming through into the chat box, and we will be addressing them as they come. I'd like to take the first question. Prof, earlier on you mentioned that I think you were implying that there's need for almost nearly every country to be doing sequencing, and you gave an example of Nigeria and Cameroon, I think, also in terms of diagnostics. I'd like to pick this question, which says, how do you work towards collecting representative samples?
Yeah, thank you. I think we did have a kind of a discussion with the Africa CDC, so I think we send information to the countries. We were basically not asking for all samples, but if you're getting representative samples, like 20% of the sample collected every week, you know, and I think that might be very helpful to have an idea of what is going on, and you know, doing some kind of genomic sequences from those will give us a better idea of what is going on. I think it is really a constant sampling, and having a weekly samples, and at least 20% should be very helpful, you know, in terms of having a deep dive into what's going on in those different environments. Over.
Thank you very much, Prof. We'll be looking forward to that guidance for selecting the samples. I'd like to also take another question from Erwan Pirio, who says, very impressive work. One question or concern is about the coverage of the sequencing, which is skewed to more accessible areas, overlapping with those areas where basic diagnostic capacity is also the most available. For many areas, this isn't the case, and turnaround time for PCR, even within Nigeria, is days or week, and the extent of the outbreak not all understood. Are there any plans to increase coverage?
Well, I do think that, you know, it's all about just organization and then what I call cooperation. It's clear that not all the labs, you know, have the ability to reduce the turnaround time. But I do believe that my lab, for instance, in Nigeria, because of the facility and the platform that we have on the ground, we provide a 24 hours turnaround time. But I think it's very important that while we're trying to move on with molecular diagnostics, I think it's very important that this molecular diagnostics could be complemented with antigen captures. If they're very good, you know, that really will be very helpful. And I think as such, I will advise that we use a combination of tests, but then there should be more coordination at the center in order to ensure that the samples get to the testing facilities, and then we can, so that we can actually reduce the turnaround time. Over.
Thank you very much once again, Prof. Moving on, we acknowledge we presented some technical information really today, and I would like to call again upon Jilian. There's a question here from Vuni Harry, who says, he's from Uganda. Can the current COVID-19 diagnostic landscape properly diagnose the current mutation? Jilian tried to summarize it, maybe for the purpose of the people who are also joining, and also a good summary. Would you try and address this question from Vuni?
Yes, it's a great question. So the current tests can detect the variants. So if someone presents and is infected with a variant, you will know that they're infected with SARS-CoV-2, but they won't necessarily distinguish the fact that it's a variant versus what is more of the wild type strain. So in order to know that you're specifically diagnosing someone who is infected with one of these variants, if they're infected with the B117 variant, and you're using an assay that detects the S gene target, you might have a a dropout of that S gene target, but you would detect the other gene targets in your assay. And so that might indicate to you that the person has the B117 variant, but it's not fully able to tell you that. The only way to know exactly the genetic sequence of the SARS-CoV-2 that is circulating within a person would be to sequence their virus. So the short answer is all the tests will still diagnose SARS-CoV-2 irrespective of whether you have a variant or not, but the current assays, most of them will not tell you which whether or not the person is infected with a variant. Hope that's clear.
Thank you for summarizing that, Jillian. Taking the next question, this is from you. He says, thanks, Prof. Happy for the great presentation. It looks like it's important for design primers to a housekeeping gene or a gene or genome section that does not change. He or she claims that I'm not a virologist, so I don't really know exactly how this is feasible. Prof.
Yeah, that's generally the ideal. You know, you don't want to design your primers in areas that are in very polymorphic areas or areas that are under a lot of water selective pressure. But again, when you design these primers, you know, you're designing them to the best of your ability, but then you also understand that, you know, the virus lives in a very dynamic system and is under different kind of pressure. So you see this accumulation occurring over time. So, and as much as possible, you really want to make sure that, you know, you're monitoring them and then that those mutations that are rising, you know, are not deleterious or that are negatively impacting, you know, your primers. Really, the idea is exactly what you said, but unfortunately, you know, we're dealing with moving target.
Yeah, moving target indeed. The next set of questions, interesting ones, of course. Any of you can keep those up. It's from Dr. Austin, Ellen, Lulawoye, and yeah, possibly Alfred Makura, and they're all related to vaccines. They say, with this level of genomic sequencing in Africa, please, what stops us from developing a local vaccine? Can the present vaccines work against variants? Are they, okay, yeah, I think those two would cover, I think, basically all of what they were asking.
Well, I will say that with the level of genetic sequencing that happens on the African continent, at least it's not that Africa is impossible. It's not impossible for Africa to design their vaccines or to develop their vaccine, but I think it's also a matter of priority. I think I've said it time for that number. If Africa really made vaccine development a priority, I'm sure that could be done. For instance, in our lab, we went on very quickly to actually have a vaccine candidate that is very promising, but unfortunately it wasn't supported within Africa. And this same vaccine candidate today is being, in collaboration with our colleagues at the University of Cambridge, is really undergoing like a phase 1 clinical trial already. And this is basically just based on genomic sequences of data that we generated from Africa, using machine learning to do negative selection, and then also to identify the most immunogenic epitopes, and then we'll go on and then do, you know, all of the in vitro and then the animal screens. So I think it's doable. So I think it's always a matter of priority, and then as you can see, it's about investment. If Africans decided to put their money where their mouth is, I'm sure, you know, we will be able to develop a vaccine. I'm sure we have the necessary skills, the necessary expertise, and then what it takes to do it. Is actually just priority and political will. Over.
Thank you once again, Prof, for that. I know it's almost time. Maybe I might take one or two more questions. And this one is coming from Julie Okonji, who is asking, due to the turnaround time challenge and limited availability of PCR-based tests, can RDT be used instead of, I think this one is talking about how we can be able to use the current available technologies. What is the test performance for antigen RDT versus PCR-based in terms of coverage as well? I think Jillian touched a bit on the impact of variants and on both the PCR as well as the antigen test. Maybe Jilian, you could take a little bit on that.
Sure. So I think there is guidance globally from WHO, Africa CDC, individual countries on how to consider using the antigen RDTs for diagnosis. The data that the limited data that is available points to the fact that these antigen detection RDTs should still be able to detect the circulating variants. For example, South Africa is using some of the antigen RDTs, and B1351 is probably the predominant SARS-CoV-2 that is circulating there now, and the antigen detection assays are working well. So I think you can, if your country or your program recommends the use of the antigen RDTs, you can feel relatively secure that there shouldn't be an issue because of any emerging variants.
Thank you, Jilian. We are nearly, I think, about 2 minutes to go. So I just like to take this opportunity to give a few moments to Prof. Happi to just summarize it for us. Just give us a few words that you'd like us to part with.
Well, I just really want to say thank you to all, to Africa CDC and ASLM for the organization of this meeting. And as you saw today, we got to learn more about the different variants circulating in Africa, and then also learn a lot about, about the different tests that are available out there. So I think the future is not dire. It's not bleak. I think there is hope despite the challenges. It is clear that, the different tests that are out there are not as bad as, people could portray. Vaccines definitely are going to work. So I think we should be very hopeful. We should encourage people to, as much as possible, to take the vaccine. But again, even with the vaccine, I want to suggest that we keep, public health safety measures, and then and ensure that together that we're all going to defeat this pandemic. It's really not just technology. It takes each and every one of us, to combat, this pandemic and then defeat COVID-19 so that we can get back to what I call a normal life. I think I really want to use this again to say a big thank you to all the presenters, and then all of the organizers, and then also the participants. Thank you.
Thank you. Jilian, in a few seconds, any last word?
No, I think Prof. Happi summarized it very well. So thank you all, and take care.
Thank you. Devi?
Same for me. Thanks, everyone. Have a great rest of the day.
Thank you. Let me also thank the presenters on behalf of ASLM for coming through and sharing with us all this valuable, important. Many thanks to all of you who have come through again to listen to what we had today in our special session. And many thanks again to our interpreter, Sarah Aichi, as usual, for the wonderful job that she always does. And I would like to also thank my colleagues for making sure that this session has gone through as smooth as it has been. I would like to just inform you that we will keep on bringing you these sessions. Next in line will be something to do with how lab information systems can be used and leveraged to fight the pandemic. Till we meet again, good morning, good afternoon, and good evening.